Have you ever really stopped to think about what happens the instant you click on a link? I mean, really think about it. Today, we're going to do just that. We're going on an absolutely incredible journey, following one tiny little piece of data as it basically teleports across the globe. So, let's trace its path together. Seriously, it feels like actual magic, right? You click, and a website from halfway around the world just appears. But you know what? It's not magic. It's a system. A brilliantly designed system of addresses, digital envelopes, and super-fast postal workers, all moving at nearly the speed of light. So how does that one little click manage to travel the entire world? You know, the best way to wrap your head around the internet is to think of it like a massive global postal service. It's just this huge collection of interconnected networks. But instead of sending letters and Amazon packages, it sends these tiny little bundles of data. Everything you do online, sending an email, watching a video, yep, making that one simple click, it all gets broken down into these little digital envelopes. And the star of our show, our main character, is this, the datagram. We'll just call it a data packet. Think of it like a postcard. It's got the message you want to send, sure, but way more importantly, it's got the destination address written right on it. Now, the internet operates on what's called a best effort basis. It's kind of funny. It doesn't actually guarantee your data will get there or even that it'll arrive in the right order. It just promises to try its absolute best to get each little postcard where it needs to go. Okay, so for this whole global postal service thing to work, every single device connected to the internet needs its own unique address. It makes perfect sense, right? Just like your house needs a street address so the mail carrier can find you, your computer, your phone, even your smart toaster needs a digital address to get its mail. And that digital address, it's called an IP address. Specifically, for most of the internet's history, an IPv4 address. It's just a string of 4 numbers separated by dots. And every single packet that leaves your computer has 2 of these addresses stamped on it. A source address that says, hey, I came from here, and a destination address that says, and I'm going way over there. But wait, you don't have to manually type this in every time you connect to a new Wi-Fi network, right? Thank goodness. That's all handled automatically by a system called DHCP. It's pretty cool. When your device joins a network, it basically shouts out into the void, hey, I'm new here, I need an address. And the DHCP server on the network, which is usually just your router, says, no problem, here you go, and leases it a temporary address from a pool of available ones. So this system sounds great. But here's the thing. It was designed decades ago, and it ran headfirst into a massive problem. The brilliant people who designed the internet, well, they just didn't imagine a world where billions of people would be carrying multiple internet-connected devices in their pockets. They started running out of addresses. This is it. This is the total number of unique addresses you can possibly have with the IPv4 system. Just under 4.3 billion. Now, back in the 1980s, that must have seemed like an infinite, impossibly large number. But today, with nearly 5 billion people online, not to mention all their phones, laptops, and smart devices, well, you can see the problem. It's just not enough. And to make things even worse, the way they handed out these addresses in the early days was, well, it was incredibly inefficient. They'd give these huge blocks of millions of addresses to a single company or university that would never, ever use them all. This classful system meant that a huge chunk of the address space was just wasted, which made the shortage happen even faster. The internet needed a clever workaround, and it needed one fast. And that brings us to the unsung hero of the modern internet, NAT, which stands for Network Address Translation. This is the brilliant, beautiful hack that keeps the internet from falling apart. Essentially, what it does is it lets all the devices in your home, your laptop, your phone, your tablet, all hide behind and share one single public IP address, the one your internet provider gave to your router. So, how does this magic disguise work? Well, when our little data packet leaves your laptop, it has a private, internal-only address, something like 192.168.1.5. As it passes through your router on its way out to the world, the router plays this amazing little trick. It erases your computer's private address and writes its own public address in the from field. And, this is the crucial part, it makes a quick note of this swap, so when a reply comes back from the internet, it knows exactly which device on your home network to send it to. And to keep track of all these quick changes, the router keeps a little list, a translation table. It's like a bouncer at a club keeping a log. It sees a packet from your laptop going to a web server and jots down the details. It sees another from your phone going to a game server and notes that too.
So when the web server replies, it sends the packet back to the router's public address. The router just checks its table, says, "Ah, this one's for the laptop," and forwards it right along. It's simple but absolutely ingenious.
All right, so our packet has its public address. It's officially out on the open internet, zipping along. Let's hit the pause button on its journey for just a second and look under the hood. What information is actually inside this digital envelope? So the header of the packet is basically the outside of the envelope. It's got all the critical info for the journey. We've got the source and destination addresses, obviously, but there's other important stuff too. The protocol tells the receiving computer what kind of data is inside, and the header checksum is a quick little math problem to make sure the address didn't get scrambled along the way. And then there's this really clever field called time to live. Time to live, or TTL, is a safety net. I mean, what if a packet gets stuck in a routing loop, just bouncing between two routers forever? That would be bad. The TTL prevents this. It's a countdown. It starts at, say, 64, and every time the packet passes through a router, every hop, that number goes down by 1. If it ever hits 0, the router knows this packet is lost and just discards it. It stops it from clogging up the internet for all eternity. Now, there's one more challenge our little packet might face on its journey. The internet isn't one single superhighway. It's this huge mesh of different kinds of networks, and some of them have strict size limits. You can think of them like low bridges or narrow tunnels. This size limit is called the maximum transfer unit, or MTU. For a standard Ethernet network, like what you probably have at home, it's usually about 1,500 bytes. So what happens if our packet is, let's say, 4,000 bytes, but it hits a part of the network with a 1,500 byte limit? It can't just squeeze through. So what does the router do? It has to break it up into smaller pieces that will fit. This process is called fragmentation. The router literally chops our big packet into smaller fragments, and each one gets its own header and is sent off like it's its own independent packet. They might even take different routes to the destination. So how does a receiving computer put the puzzle back together? Well, the original packet gives all its baby fragments the same identification number. This is like a serial number that tells the destination computer, hey, all of us belong together, which allows it to reassemble everything back in the correct order. Okay, our packet is almost there. It's crossed oceans and continents, it's navigated countless routers, it might have even been chopped up and put back together. Now we are at the final step, local delivery. But just like with physical mail, things can still go wrong at the last second. So, to understand this last little hop, we need to know about one more type of address. Your device has its IP address, which is like its street address. It's logical, it can change, but it also has a physical MAC address. This is burned right into its network hardware. It never changes. It's like the specific name on your apartment door. The IP address gets a packet to the right building, but the MAC address gets it to the right apartment inside. So when a packet finally arrives at the destination network, the local router knows the final IP address it's looking for, but it still needs to find the specific device with that address. To do that, it uses something called the Address Resolution Protocol, or ARP. It basically broadcasts a message to every device on the local network asking, hey, who has this IP address? And the one correct device replies, yo, that's me, here's my permanent physical MAC address. And with that, the router can finally make the delivery. But what if the server's offline? Or what if our packet's TTL countdown hits 0? The internet needs a return-to-sender system, right? And it has one. It's called ICMP, the Internet Control Message Protocol. It's just a dedicated system for sending error messages. If a destination can't be found, an ICMP message comes all the way back saying destination unreachable. This is also the protocol behind the ping command that some of you have probably used, which just sends a little echo request to see if another computer is online and can reply. And that's it. Our packet's journey is complete. From one single click, it was assigned an address, wrapped in a header, disguised by a router, sent across the world, maybe fragmented, then reassembled, and finally delivered using its physical address. All of it happening in less time than it takes to blink. It is an unbelievably complex and beautiful dance. You know, the IPv4 system, especially with its brilliant NAT workaround, has served us incredibly well. It is the foundation of the internet we know and love today. But as we start connecting trillions more devices to the internet, everything from our cars to our coffee makers, it's pretty clear this 40-year-old system is creaking at the seams. So is it really built for tomorrow? Well, that's probably a journey for another day.